Good morning, students. In the last video we have seen about photoelectric effect. This is a question which has appeared in 2020 IIT JAM paper. Okay, that is last year's paper. That is okay. A monochromatic light is incident on a metal plate and photoelectric effect occurs. Okay, when the power of the source is doubled. Okay, what happens is asking number of photoelectrons emitted decreases, stopping potential gets doubled, the photocurrent remains same. Okay, stopping potential remains same. These are the four options. A straightforward question. Okay, when a monochromatic light is incident on a metal plate and photoelectric effect occurs. Okay, photoelectric effect is occurring means the energy of the incident photons is more than the the work function of the metal. That's only when the photoelectric effect occurs. Okay, when the power of the source is doubled. Now just guess what will be the answer. Straightforward, simple question for 1 mark. Okay, you don't have to put pen on paper, simply read and put the answer here. What happens? Number of photoelectrons emitted decreases when the power is increased according to quantum theory. Okay, power is increased means number of photons emitted per second is doubled. Okay, power is doubled means number of photons will get doubled, so number of electrons also will get doubled. So the number of photoelectrons emitted decreases. This is not the right option. Okay, this is not the right option. Next one, stopping potential gets doubled. Stopping potential does not depend on the intensity of incident light. Stopping potential depends on the maximum kinetic energy of photoelectrons. That's what we have seen yesterday, right? K maximum is equal to EVS, we have seen, is equal to h nu minus phi. That's how we have written the Einstein's photoelectric equation. So nothing, stopping potential, when you are doubling the power means intensity is getting doubled. Okay, stopping potential will not get affected, so this option is also not correct. The photocurrent remains same. When the number of photons incident on the metal plate increases, number of electrons emitted also will increase, so photocurrent obviously increases. Okay, so photocurrent cannot remain same, so this option is also wrong. When three options are not correct, obviously fourth one should be the answer. Okay, right, stopping potential remains same. Stopping potential is not affected by the intensity. Stopping potential is affected by the frequency of incident light. If the frequency of incident light is doubled, then stopping potential will get doubled or will increase. Here, right, frequency is not affected. We are simply increasing the power of the source is doubled. Means intensity is getting doubled. So stopping potential remains same. So this is our option. Straightforward, simple question. Okay, right, now we'll go to another question which has appeared in same 2020. Right, IIT JAM physics paper. Another simple question without putting pen on paper. You can solve this also. Okay, just read this question. 5 non-interacting electrons are present in a one-dimensional infinite potential well of width A. The highest energy of the particles is. Okay, infinite potential well, particle in a 1D box. Okay, right, of width A. 5 non-interacting electrons are there. Okay, right, the highest energy of the particles is asking. We will see the answer for this. Straightforward. Directly you can put the answer at the end. We will come back to this problem. Okay, now I will continue with our what you call photoelectric effect. Compton effect. Okay, right, so our today's topic is Compton effect. Okay, Compton effect. What has been observed is when a monochromatic X-ray beam of wavelength lambda, monochromatic single wavelength. Okay, when a monochromatic X-ray beam of wavelength lambda is sent on to a target of low atomic weight, the scattered secondary radiation, right, found to contain two wavelengths. Okay, one is the same wavelength as that of the incident beam and the second one is slightly longer wavelength. Okay, means I'll take a target of low atomic weight. This is my target. Okay, I'm sending a monochromatic X-ray beam of wavelength lambda. This is X-ray beam. Okay, X-rays of wavelength lambda. The scattered radiation in any direction if I see, scattered radiation is found to contain two wavelengths, one having the same wavelength lambda as that of the incident beam, and the second one is a slightly longer wavelength lambda dash. Okay, right? Now this is known as incoherent scattering, we call. Scattering is what? Light going and falling on something and getting spread out in all directions is known as scattering. The scattering will be of two types. When the what you call, after getting scattered, if the wavelength of the incident light changes, right, it is known as incoherent scattering. If the wavelength of the incident light remains same, it is called coherent scattering. Okay, so scattering is of two types. When light beam goes and falls on some target and gets scattered in all directions, okay, and in any direction if you see, you are finding the same wavelength what you have sent, okay, there is no new wavelength, that is known as coherent scattering, right? If there is any change in wavelength, let it be increase in wavelength or decrease in wavelength, it is known as incoherent scattering. Okay, the scattering of light which is responsible for blueness of sky, or why sky is blue, why sea waters, oceans appear blue in color, why during sunrise and sunset sun appears red in color, okay, why skylight is predominantly plane polarized. Okay, the answer for all these questions is scattering of light, we say. And if I go slightly deeper, what type of scattering it is known as coherent scattering, called Rayleigh scattering. Okay, where white light from sun comes, right, interacts with our atmospheric molecules and gets scattered in all directions. In any direction you see, there won't be any new wavelengths coming. What all wavelengths that are incident only will get spread out in all directions. Okay, means what? Wavelength is not changing means frequency is not changing. When frequency is not changing means the energy of the incident light is not changing, right? After getting scattered from a medium, right, energy of the incident light is not changing means energy of the medium is also not changing, means medium will not get affected by the propagation of radiation. Okay, we can go and see why, as we are going high on the what's called altitude, at higher altitudes or on mountain caps, we will find snow. Okay, when we are going away from the earth's surface at higher and higher altitudes, temperature keeps on falling down. Okay, right? But we are approaching closer to sun, temperature should increase, isn't it? But what happens as you are going up, right, temperature keeps on decreasing actually, because though we are getting closer to sun by 5 kilometers or 10 kilometers or 50 kilometers, okay, medium is not getting affected by radiation, right? It is coherent scattering we call. But here what is happening, when I am sending a monochromatic X-ray beam of wavelength lambda, after scattering in every direction I am finding new wavelengths. One is two wavelengths, one is lambda and other one is lambda dash, means this new wavelength is coming. Okay, the component which is having same wavelength as that of the beam, that of the incident beam, is called unmodified line. Okay, unmodified line, and the wavelength lambda dash which is slightly longer than the incident wavelength is called a modified line. Okay, modified line. Okay, this means what? When new wavelength has come means this Compton effect is incoherent scattering phenomenon. Okay, wavelength is getting affected. The component which is having same wavelength as that of the incident beam is unmodified line, or Thomson component we call. Okay, Thomson component, because Thomson, the scientist, with the help of classical wave theory of light only, he could successfully explain how lambda comes, but he could not explain why lambda dash is coming. Why lambda dash is coming could not be explained. So unmodified line or Thomson component, because Thomson could successfully explain the existence of lambda after scattering, but he failed to explain why new wavelength, slightly longer wavelength lambda dash is coming, means modified line could not be explained by classical theory. Okay, so Compton was the first scientist, okay, to use what you call Max Planck's quantum theory, and he could successfully explain this Compton effect. According to Compton went a step ahead of Max Planck and Einstein or even Niels Bohr. Okay, even Einstein took it as simply a packet of energy, that's all. Localization of energy, he said. He did not elaborate anything about the photon. Even Max Planck considered it as an ad hoc hypothesis, okay, to explain black body radiation. But what is the nature of that photon? Okay, what is the meaning of the frequency of a single photon, right, could not be understood in the initial stages. Okay, even Max Planck did not understand, Einstein never talked about it. Okay, Niels Bohr also did not talk about it. They simply took it as packets of energy and they were successful in explaining some phenomena. Okay, Max Planck could explain black body radiation, Einstein could explain photoelectric effect. Okay, Niels Bohr could explain the spectrum of hydrogen atom. Okay, but they have not elaborated the nature of the photon. They have simply considered it as packet of energy. Okay, but Compton went a step ahead. He said, we need not call it as simply a packet of energy. You can consider it as a pure particle. Okay, pure particle. What are the moment I say a particle, what are the properties of a particle? Every particle should have some mass m. Okay, the moment it starts moving, it should have a momentum p, right, is equal to mass multiplied by its velocity. Then immediately the question comes, what is the mass of each photon? What is the momentum of each photon? Okay, now what Compton said is, right, according to quantum theory, E is equal to h nu. According to relativity, E equal to mc square. So photons energy is h nu according to quantum theory. Photons, right, according to relativity, energy is always equal to mc square. So he said mass of each photon can be taken as h nu by c square. Okay, means any photon of energy h nu can be considered as a particle whose mass is h nu by c square. Okay, right, that's why mass units are, what are the units of energy h nu, right, electron volt by c square. EV by c square is a unit of mass in particle physics. Okay, next, what is the momentum of the photon? Photon travel with, photon means light particle, light travels with velocity c. So mass h nu by c square into the velocity of photon is c. This becomes the momentum of each photon is equal to h nu by c, we write. Okay, every photon of energy h nu can be considered as a particle with mass h nu by c square and momentum h nu by c. Okay, not only saying that, he has applied the conservation of momentum principle to light. He was the first scientist to apply conservation of momentum principle to light. Okay, now in particle physics, this has become the unit of momentum, right? H nu units are electron volt by c. EV by c is taken as unit of momentum in particle physics, nuclear physics, particle physics. Okay, EV by c square becomes unit of mass for particles, elementary particles. Okay, so photon now has some momentum. Okay, photon has some momentum and mass also. So he has applied the conservation of momentum principle apart from conservation of energy. Now we take the situation like this, a target. Okay, now this photons are going and what you call hitting the target, means inside the target what will we have? We'll have atoms. Inside the atoms what do we have? Right, one nucleus and one electron revolving, some electrons revolving around the nucleus. The incident photon, in order to get scattered, the size of the scatter should be greater than the wavelength of incident light. Okay, so our photons are getting scattered from the atoms, means inside atom we have nucleus and electrons, right? Nucleus is extremely small. Okay, the size of the nucleus is lakhs of times lesser than the size of the atom. The volume of the atom is nearly 10 to the power 15 times, 1 billion million times more than the volume of the nucleus. Okay, so we cannot expect nucleus to scatter the incident photon. So what else can scatter? It is only the electrons, means our photon will go and interact with the electron inside the atom. So I take this as the target electron. Okay, target electron. Compton assumed that the target electron is at rest. Okay, is at rest means it will not have any kinetic energy. Okay, it is a free electron, so it will have only free electron, means what? It will not have any potential energy. Okay, it is at rest, it will not have any kinetic energy. Then what type of energy it will be having? Only the rest mass energy, m naught c square. So the target electron has simply rest mass energy, m naught c square. Our incident photon of energy h nu and momentum h nu by c, right? This is our incident photon. Okay, goes and hits the target electron, right? And it gets scattered like this, making an angle theta with the incident direction. Okay, this is the direction in which the scattered photon moves. Okay, scattered photon. Now after scattering, okay, after scattering, the photon's energy becomes h nu dash and momentum becomes h nu dash by c. Okay, this is our scattered photon, and this electron right gets recoiled, making an angle phi with the initial direction. This is recoil electron. Okay, its mass is m, so its energy will be mc square. Its momentum will be, it is moving with some velocity v, its momentum will be mv. Okay, right, this is how Compton has visualized. So what are the assumptions made by Compton? That is an interaction between the incident X-ray photon and the electron. The target electron is assumed to be at rest and is a free electron. Both of them are not actually true, but initially considered like that. Later on we can make small modifications. Okay, right, the target electron is assumed to be rest and is a free electron. Our incident photon of energy h nu, momentum h nu by c, goes and hits that electron. What could not be explained by classical wave theory at all could be explained by quantum theory very easily. In just 2 sentences we can explain. Okay, classical wave theory of light could explain why lambda is coming, but why longer wavelength lambda dash is coming could not be explained by classical wave theory. Okay, according to quantum theory, light is in the form of a photon of energy h nu and momentum h nu by c. A photon of energy h nu goes and strikes the electron, gives some of its energy to the electron. Okay, gives some of its energy to the electron, gets scattered with lesser energy. Photon's energy is decreasing means what is decreasing? Frequency should decrease. When frequency decreases, what should happen to wavelength? Wavelength increases. That's all. That's how we are getting lambda dash inside. Okay, then what will happen to this electron? Electron is getting some energy from the incident photon. That electron recoils with that whatever kinetic energy it has gained from the incident photon. Means what could not be explained by classical wave theory at all could be explained by quantum theory in just 2 steps like this. A photon of energy h nu goes and strikes the electron, gives some of its energy to the electron, not all energy. Okay, some of its energy to the electron, gets scattered with lesser energy, lesser momentum, means that is right, lesser frequency, that is longer wavelength. Why lambda dash is coming could be explained. Okay, so this is the Compton effect diagram. Now I'll apply conservation of energy and conservation of momentum. Okay, Compton treated as a collision between 2 particles. One is the target electron, which is assumed to be at rest and is a free electron, and the incident photon. Incident photon is also having some mass h nu by c square and momentum h nu by c. So it is 2 particle interaction. Okay, right, now when I apply conservation of energy principle, what is conservation of energy principle? Total energy before the collision must be equal to total energy after the collision. What is total energy before the collision? Right, there are only 2 particles involved, incident photon and target electron. What is incident photon's energy? H nu, plus what is target electron's energy? It is not having any kinetic energy, it is not having any potential energy. The only energy possessed by the target electron is its rest mass energy m naught c square. So the total initial energy is h nu plus m naught c square is equal to the total final energy after the interaction. What is the energy of the scattered photon after the interaction? H nu dash plus what is the energy of the recoiled electron? Mc square. Okay, so total energy after the interaction is h nu dash plus mc square, right? Total energy before the interaction is h nu plus m naught c square. I'll take this as equation 1. Next I'll apply conservation of momentum principle. Okay, momentum is a vector quantity, right? I'll split up into x component of the momentum and y component of the momentum. Okay, now photon is initially, what is photon's momentum? H nu by c. It is initially moving purely along the x-axis only. So what is its x component of momentum? Entire momentum is along the x-axis only. So total initial momentum along the x-axis h nu by c plus the target electron is at rest. It is not having any momentum initially, so 0. Okay, is equal to, after the collision, the photon is getting scattered like this. Now I'll split that into horizontal and vertical components. The momentum is h nu dash by c. This angle is theta, so the adjacent component or horizontal component becomes h nu dash by c cos theta. This is the component of momentum along x-axis after the interaction. That is, right, photon's momentum becomes h nu dash by c cos theta plus, right, electron is moving like this. Okay, electron total momentum is mv. Now I'll split this into two components, horizontal and vertical components. What is this horizontal component? Then this angle is phi, this angle also will be phi. Okay, so this component will be mv cos theta. So mv cos theta, cos phi. Okay, this is called recoil angle, this is called scattering angle. Okay, this is momentum conservation along x-axis. Now what is momentum conservation along y-axis? Photon is initially moving only along the x-axis. So what is its y component of momentum? 0. Okay, plus electron is not having any momentum at all because it rests. What is its momentum? Again 0 is equal to, what is the y component of the momentum of the scattered photon? When this is h nu dash by c cos theta, this will become h nu dash by c sin theta. So it is h nu dash by c sin theta plus. Okay, now what is y component of the momentum of the electron? It is mv sin phi, we write. Okay, but this downward y direction is negative y axis. Okay, upward if I take it as positive, this is downward direction, so it is negative y axis. So I have to put minus sign here. Okay, minus mv sin phi. Okay, so these are the three equations. Okay, one is due to conservation of energy, other one is two components of the momentum along x-axis and along y-axis. Okay, now what is our aim? Our aim is to find out what is the frequency of the photon after the interaction. I want to find out nu dash, or in terms of what you call wavelength, I want to find out what is happening to lambda. Okay, what is the final wavelength lambda dash we want. Okay, when I am sending lambda, what is happening to lambda and how am I getting lambda dash I want. So our interest is in nu dash. Now what do I do? Wherever m is there, because I am using relativity concept here, m equal to m naught by root of 1 minus v square by c square, relativistic variation of mass with velocity also I'll consider. Okay, I'll rearrange the terms here. Okay, whenever we have sin phi and cos phi terms, what do? We will square them and add them such that sin square phi plus cos square phi, right, becomes one parameter will be eliminated. Okay, doing all those manipulations, finally what do we get? Okay, finally we get like this. Lambda dash minus lambda equal to, right, d lambda equal to h by m naught c into 1 minus cos theta. H by m naught c into 1 minus cos theta, this is c. Okay, right, lambda dash is the modified wavelength, lambda is unmodified wavelength. What is lambda dash minus lambda? Change in wavelength. Okay, d lambda, this is called Compton shift. This is called Compton shift. D lambda equal to, right, h by m naught c into 1 minus cos theta. This is the final result. This is the final result what we'll be getting. Okay, after making all the manipulations, simplifying, squaring and adding, etc. Lambda dash minus lambda equal to d lambda equal to h by m naught c into 1 minus cos theta. Now look at this expression. What do we understand from this? Compton shift d lambda, that is change in wavelength in Compton effect, right, is depending on what factors? H is a constant, rest mass of the electron is a constant, c, velocity of light is a constant, theta, that is, it depends only on the scattering angle theta. It is independent of the nature of the target. Okay, it is independent of the incident wavelength, it is independent of all other factors, it depends only on the scattering angle theta. So right, Compton shift d lambda is whatever lambda you send. Okay, change in wavelength will remain same. Whatever is the target element you put, change in wavelength will remain same. Change in wavelength depends, Compton shift depends only on the scattering angle, nothing else. That is the most important conclusion we can draw. Okay, now from this it depends only on theta. That is what is understood now. Okay, so what happens, right, I'll keep putting different values of theta and see how much is the Compton shift. Now be careful, in the examination Compton shift d lambda is independent of the incident wavelength, but sometimes what do they do, right, in Compton effect the scattered wavelength lambda, what is scattered wavelength lambda is equal to lambda plus d lambda. See, d lambda is independent of lambda, but lambda dash depends on lambda only. Okay, be careful whether it's asking for, right, d lambda or lambda dash. Lambda dash depends on incident wavelength. Okay, but Compton shift d lambda is independent of the incident wavelength. Okay, so Now I'll put case 1 theta equal to case 1 theta equal to 0 degrees. Okay, what happened? Cos 0 is 1, 1 minus 1 is 0, lambda dash minus lambda, d lambda equal to 0. Okay, means lambda dash equal to lambda, means in the direction of the incident photon, when theta is equal to 0, right, there is no Compton shift. Okay, Compton shift does not exist. Okay, next one, I'll put theta equal to, second point, theta equal to 90 degrees. When I take theta equal to 90, cos 90 equal to 0, right, lambda dash minus lambda equal to d lambda equal to, what do we get here? H by m naught c. H by m naught c. Okay, it is a constant. Okay, right, H is Planck's constant, rest mass of the electron 9.1 × 10 to the power minus 31 kg is constant, c, velocity of light is also constant, means d lambda equal to h by m naught c. Now what will be the units of h by m naught c? Is nothing but equal to d lambda, no, so it will be centimeters. What is the dimensional formula of the term h by m naught c? Length dimensions. Okay, what are the units? You can take them as angstroms or centimeters or whatever it is. Okay, h by m naught c, if I substitute these values and simplify, I'll get 0.0242 angstroms. Okay, right, 0.0242 angstroms. Right, d lambda equal to, this is one very important result which you have to memorize. Okay, Compton shift when theta equal to 90 degrees is equal to how much? H by m naught c. Okay, what is h by m naught c? H by m naught c nothing but Compton shift when theta equal to 90 degrees. So directly in the examination, what are the dimensions of h by m naught c term? It is having length dimensions. What is the value of h by m naught c? 0.0242 angstroms, or you can write it as 2.42 picometers. 2.42 picometers also you can take. Pico means 10 to the power minus 12. Angstrom means 10 to the power minus 10 meters. Okay, right, this is called Compton wavelength lambda c. Compton has specially given his name to this Compton shift. Okay, when theta equal to 90 degrees, this is called Compton wavelength. So wherever h by m naught c is there, you can write it as lambda c. So how much is lambda c? 0.024 angstroms. What is the significance of this one means? This 0.024 angstroms corresponds to the rest mass energy of the electron. Okay, right, what is rest mass energy of the electron? Rest mass is m naught, right? According to relativity, rest mass energy is equal to m naught c square. This is how much? 0.511 MeV. Okay, rest mass energy of the electron is 0.511 MeV. Means what? How do we understand? If you smash one electron completely, because it has that much of mass, 9.1 × 10 to the power minus 31 kg, if somebody smashes the entire electron's mass in the universe, how much energy gets released? 0.511 MeV of energy, MeV energy gets released. Okay, what that energy will be in which form? It will be in the form of radiation. What is the wavelength of the radiation whose energy is 0.511 MeV? We'll use the formula E equal to 12,400 by lambda. Lambda equal to 12,400 by, if I take 0.511 million electron volts and simplify, I'll get 0.0242 angstroms. Means the wavelength of the photon, right, emitted when somebody smashes an electron completely in the universe, though it is impossible. Okay, right, how much it will be? 0.0242. That is found to be accidentally equal to the Compton wavelength. Okay, so that is a significance. It does not mean that here electron is getting destroyed. No, nobody can destroy a single electron. Okay, right, coincidence is that the lambda c is corresponding to the rest mass energy of the electron. Okay, these things will become useful once we go into particle physics. Okay, remember this, in pair production, etc. These things will become very useful. Wavelength corresponding to 0.511 MeV is 0.024 angstroms. In pair annihilation, an electron and a positron both get destroyed, so total energy will be 0.511 into 2, 1.02, 12,400 by 1.02 MeV, 0.0121 angstroms, like that. Okay, right, now So of course this has nothing to do with the destruction of electrons or pair annihilation, anything. It's a coincidence that h by m naught c value is 0.0242 angstroms, that is equal to the rest mass energy of the electron. Okay, that's why Compton has given a special name and it is known as Compton wavelength, denoted by lambda c. So wherever h by m naught c is there in the formula, now I can replace that with lambda c also. Lambda c value can be directly taken as 0.0242 angstroms. Okay, so I'll write now this expression as, right, d lambda equal to lambda dash minus lambda equal to Compton shift d lambda equal to lambda c into 1 minus cos theta, we can write. Okay, directly where lambda c is h by m naught c, what is its value? 0.0242 angstroms. Okay, now I'll take another value for theta, right? Theta equal to 180 degrees I'll put. Okay, when theta equal to 180 degrees means what? Photon is going like this and getting scattered in the backward direction. Okay, the angle is 180 degrees. Okay, for completely backward scattering, theta equal to 180 degrees. Cos theta equal to how much? Cos 180 minus 1. 1 minus of minus 1. It will be equal to 2 lambda c. That is lambda dash minus lambda equal to d lambda equal to 2h by m naught c, or 2 lambda c, right? How much is lambda c? 0.0242 angstroms. So what is 2h by m naught c, right? 0.0484 angstroms. This is the maximum possible Compton shift, remember. Okay, d lambda equal to, right, 0.0484 angstroms is the maximum possible change in wavelength in Compton effect. Okay, right? So right, when will that occur? When the photon gets scattered in backward direction, means after hitting the electron, if the photon comes back straight, right, then the angle of scattering will be 180 degrees. In that case, the change in wavelength of the photon is maximum. But by how much it changes? 0.0484 angstroms, or 4.84 picometers. Okay, this is the maximum possible change in Compton shift. Even in problems, theta can be given as, what you call, theta can be taken as 30 degrees, theta can be 60 degrees, theta 90 is already known. Okay, you can take theta as 120, 150, 135 degrees, 180, like that. Okay, 180, right, 90 and 0 we have seen. Put other values. Take theta equal to 60 degrees. Cos 60 is how much? Half. 1 minus half is half. Half into lambda c, 0.0242 by 2 means 0.0121. Okay, so what is Compton shift when the scattering angle is 60 degrees? 0.0121 angstroms, like that. Okay, right, now this is about Compton effect. Okay, now we'll go slightly beyond the result. Okay, what we will see what is beyond this formal expression. Okay, I'll put it in the form of additional points. I'll put it in the form of additional points. The first one is, the first point, in photoelectric effect, we have seen that the energy of the incident photon is h nu is approximately equal to phi. Okay, is the order of the binding energy of the electron. Therefore, the electron is considered as a bound electron. Here, which type of photons I am sending? I am sending X-ray photons. X-ray photons means the X-ray wavelength range is about 0.1 angstroms to, right, about 10 angstroms. Okay, right. Now, what is the energy of a photon whose wavelength is 1 angstrom? When lambda equal to 1 angstrom, what is the energy of that photon? I told you, right? The formula is energy equal to 12,400 by lambda. If lambda is in angstroms, energy will directly get in electron volts. So, X-ray photon's wavelength is 1 angstrom, means 12,400 by 1, right? The energy of the photon is 12,400 electron volts. Okay, right? Now, what is the energy of visible light photons? Visible light photons energy is from 1.7 electron volts to 3.1 electrons only. Now, compare that with the X-ray photons energy, 12,400 electron volts. Okay, right? If I send an X-ray photon of wavelength 0.1 angstroms, then what will be the energy? Right? 12,400 by 0.1, it will be 1,24,000 electron volts. Okay, 1,24,000 electron volts means what tremendous energy X-ray photons have, you see. Okay, they have tens of thousands of electron volts. When photons with tens of thousands of electron volts go and fall on an electron which is revolving around the nucleus in some atom, what will be the binding energy of the electron? Okay, if it is an outermost electron, its binding energy will be hardly 5 to 10 electron volts only. So an electron bound with 5 to 10 electron volts is being hit by a photon with energy tens of thousands of electron volts. That photon feels that this electron is completely free electron. It won't bother about the extremely small binding energy of this electron. When you go and ask that photon, it says this electron is free only. Okay, just like you are trying to tie a big Alsatian dog with a sewing thread. Okay, the energy of the Alsatian dog, right? Sewing thread is, now you have to use some big chain, okay, to hold that dog. Okay, you cannot use one sewing thread or some other normal thread and think that it is bound. Though a fish technically it is bound only, but can that string stop that dog? No, impossible, isn't it? So it is free dog only. Okay, same is the case here also. Electron is, right, bound to the atom with just 5 electron volts of energy. You are sending a photon of 10,000 electron volts. Okay, 10,000 electron volts photon. This 5 electron volts binding energy is nothing. So this electron immediately and easily comes out. So here what happens is, the first additional point is like this. Okay, here in Compton effect, the energy of the incident photon h nu is very much greater than phi. Phi is the binding energy of the electron. Okay, right? H nu is very much greater than phi, thousands of times more than the binding energy of the electron. Therefore, okay, right, the electron is considered as a free electron. Okay, strictly speaking, the electron is actually bound to the atom revolving around the nucleus. Okay, but with respect to the energy of the incident photon, that electron can be considered as free electron only. That's the reason why Compton actually took it as a free electron. Though no electron in atom is completely free. Electrons are bound to the nucleus, no doubt. Okay, but still, here it be becoming a free electron. So in Compton effect, the electron is a free electron. In photoelectric effect, the electron is a bound electron. Okay. Now, second point is, a free electron cannot absorb all the energy of the incident photon. Cannot absorb all the energy. This is an important point. All the energy of the incident photon. Okay. Free electron cannot absorb all the energy of the incident photon. Take this as an assignment. Okay, use conservation of energy, means photon's energy is how much? H nu. Okay, that should go to the electron. Electron's energy becomes mc square. Okay, use conservation of momentum principle, conservation of energy principle, right? You will not get what you call m equal to m naught by root of 1 minus v square by c square. Okay, that equation will get what you call will not be satisfied. So we can prove that free electron cannot absorb all the energy of the incident photon. When the free electron cannot absorb all the energy of the incident photon, what will happen? Photon is coming and hitting the electron. Our electron cannot absorb the entire energy of this photon. So what will happen? It will take only a part of the energy, right, and get scattered with lesser energy. Okay, right, electron takes only a part of the energy and recoils. What happened to our incident photon? Incident photon has lost only a small part of its energy and it gets scattered with lesser energy, lower frequency, longer wavelength. Okay, that's how we are getting lambda dash. Okay, right, now a free electron cannot absorb all the energy of the incident photon. Therefore, what will happen? Right, after the interaction, both, right, electron, target electron and incident photon appear. Okay, right, because our photon's energy is not getting taken by the electron completely. Our photon is still having some energy, so it also appears. So after the interaction Compton effect, right, both electron and photon will be appearing. Okay, in the examinations also questions will come on. a photon interacts with a free electron. Okay, whenever I use the word free electron, it is Compton effect. In Compton effect, after the interaction, photon disappears, electron disappears, both disappear, both appear. Okay, in photoelectric effect, photon disappears because there the electron is a bound electron, photon loses all its energy to the electron, disappears after the interaction. Here, photon also appears, means here both electron and photon appear. Okay, that's one important aspect. Okay, right, next one. Okay, you can take this as a simple assignment. Okay, using conservation of energy principle and conservation of momentum principle, try to get the relation between m and m naught. M and m naught are related as m equal to m naught by root of 1 minus v square by c square. You won't get this relation. If the entire energy of the photon h nu goes to the electron, you won't get this result for m. Okay, you are not getting this result means what? Right? That is not possible. Means entire energy of the electron, photon cannot go to the electron. Okay. The fourth point in this is we have explained why lambda is coming. Okay, why lambda dash is coming, but why lambda is also coming in every direction, right? Both lambda is coming. This is the incident photon direction. This is the target electron, say at 90 degrees. Okay, lambda dash is also coming, but lambda also will be there. Lambda dash will be lambda. Okay, what is change in wavelength d lambda? 0.0242 angstroms. Okay, but lambda is also there. We have seen, right, why lambda dash is coming till now, but why lambda is also coming means the situation is like this. Our photon is going and hitting the electron. Electron is present inside the atom. Inside the atom, there will not be, right, a single electron, but some many electrons will be there. Nucleus is like this. Electrons are revolving in various orbits around the nucleus. Okay, some electrons are in first orbit, some electrons are in second, third, fourth orbits, like this, say. Okay, electrons which are in first orbit are very tightly bound to the nucleus, than electrons which are present in the outermost orbit. Outermost electrons are very loosely bound. Their binding energies will be simply about 5 to 10 electron volts only. But as I am going deeper and deeper into the atom, the binding energy of the electron keeps on increasing. The innermost electrons may be bound by some 20,000 electron volts, or even 20,000, or even 30,000 electron volts also. Okay, the binding energy may be 30 kV also. Now I am sending a photon. Okay, that to which photon? It is X-ray photon. X-ray photon's energy is around, suppose say 12,000 electron volts. Okay, 12 keV. If our 12 keV photon goes and hits an outermost electron in the atom, that electron becomes a free electron. Okay, Compton effect takes place. I am getting lambda dash. This electron takes some of the energy of the incident photon, gets scattered with, right, lesser energy, lower frequency, longer wavelength, etc., etc. Okay, but there is no rule that every time the photon which I send should go and hit the outermost electron only. What happens if the photon goes and hits the innermost electron? Okay, when our photon goes and hits the innermost electron, its innermost electron's binding energy is about 20,000, 30,000 kV, comparable to or even more than the energy of the incident photon. Now what will happen? This electron is so tightly bound to the nucleus or to the atom that, right, it won't come out. Right, the collision becomes a collision between, right, the photon and the entire atom. It is not a collision between this electron, this photon and simply an electron, because electron is very tightly bound. Entire atom recoils. Entire atom recoils. Okay, it is like this. It is like this. Say this pen is on this calculator. Okay, simply lying on the calculator. Okay, it is not bound to the calculator. When I hit this pen with my hand, what happens? Nothing will happen to the calculator. Pen will go and fall off somewhere. Means it can be treated as a collision between my hand and the pen only. If the electron is outermost electron, which is very loosely bound, our photon goes and hits the electron, it becomes this case. It is a collision between the photon and the electron. Okay, but suppose say I'll fix this pen to this calculator, or this is a heavy table. Imagine this to be a heavy table, right? I'll fix this with quick fix, or I'll fix some screws. Okay, that this pen is very tightly bound to the table. Table is about 1000 kg. Say. Now my hand, I'll go and hit this pen. Okay, do you expect this pen to go and fall off directly? No. Okay, what will happen? As this pen is tightly bound to the table, it becomes a part of the table, then the collision is between my hand and the entire table. So what will happen? It is not the electron which recoils, entire table recoils. Okay, if I go and hit it forcefully, it is not electron going that side, my hand will break and fall this side, because it is a collision between my hand and the entire table. So who is recoiling now? Okay, entire table is recoiling. Similarly, here, when the innermost electron is hit with our photon, it is the entire atom which is shaking or recoiling. Okay, so in the formula, right, d lambda equal to h by m naught c into 1 minus cos theta. This m naught is the rest mass of the recoiling particle. If the recoiling particle is simply an electron, I'll put the electron's rest mass. Okay, but in this case, what is happening? Entire atom is recoiling. Okay, so I have to put the rest mass of the atom here. When I put the rest mass of the atom, what will happen? Atom means what? Nucleus also comes into picture. Nucleus contains what? Protons and neutrons. Each proton's mass itself is about 1836 times the mass of the electron. Mass of one proton is 1836 times. If its atomic number is say 30, okay, there will be 30 protons, and definitely about more than 30, around 40 or 50 neutrons will be there. Nearly 80 nucleons will be there. 80 into each nucleon is about 1800 times more. Say roughly 2000. 80 into 2000, 1,60,000 times more mass. Means here I have to put d lambda is how much? When I put m naught, I am getting 0.0242. When I divide it with 1,60,000, first of all, the change in wavelength itself is 0.0242. Divide it with 1,60,000, 2 lakh, 3 lakhs, what will happen? It's almost 0.00000 nothing. Okay, there is no shift. Means d lambda is almost 0. Lambda dash will be equal to lambda. We'll get unmodified line. Now we can understand why we are getting both modified and unmodified lines. When do I get modified line? When the incident photon strikes the outermost electron in the orbit. Okay, we get lambda dash. When our incident photon goes and strikes the innermost electron in the orbit, okay, we'll get lambda. We'll get lambda. That's why, though Compton shift d lambda is independent of nature of the working substance, nature of the substance or nature of the target, right, we have to take target of low atomic weight. Okay, if I take a target of high atomic weight like tungsten, Z equal to 40, 50, 60, molybdenum, etc., 50 electrons will be tightly bound, hardly 2 or 3 electrons will be loosely bound. Loosely bound electrons only will give me lambda dash. Okay, remaining all are tightly bound electrons only. They give me mostly lambda. Means when I am doing Compton effect experiment, I expect to see this change in wavelength lambda dash mostly. I don't want lambda. I don't want to observe lambda mostly. I want to observe lambda dash. I want more lambda dash means more free electrons should be there. Okay, then only lambda dash will be more. Intensity of lambda dash will be more. Okay, so what happens when I take a target of high atomic weight? Most of the electrons are tightly bound. They will be giving me mostly lambda only. I will be getting very less intensity lambda dash, which is difficult to measure. So in order to have what you call lambda dash with maximum intensity, right, I should have a target where the electrons are free electrons mostly. That's why target of low atomic weight, if I consider, hardly 5 or 6 electrons are there in the atom. All 5 or 6 electrons are loosely bound only. So I will be observing mostly lambda dash, very less lambda. Therefore, why we have to choose target of low atomic weight? In order to have the intensity of lambda dash maximum. Okay. Right, so a question can come like this: as the atomic number Z of the target element increases, what will happen? As the atomic number Z of the target element increases, okay, the intensity of lambda dash modified line decreases, the intensity of unmodified line increases. Okay, right, this is one point which you have to remember, right? As the atomic number Z or atomic mass A of the target element is increased in Compton effect, what will happen? Intensity of the modified line will decrease, intensity of the unmodified line will keep on increasing. Okay, but whenever I am doing Compton effect experiment, I want to have more intensity for modified line. Lambda dash should be more, okay, in intensity. That's why it is preferable for me to choose target of low atomic weight. That's another point, okay, in Compton effect. Next one, why should we do this experiment with visible light only? With X-rays only. Why can't I do it with visible light just like I did in photoelectric effect? Okay, Now in theta equal to 90 degrees, what is d lambda? D lambda is lambda dash minus lambda equal to, how much did we get? 0.0242 angstroms. Say I'm using 1 angstrom wavelength X-rays. Okay, so lambda equal to 1 angstrom. Lambda d lambda is 0.0242. So what is the scattered wavelength? Right? What is lambda dash? Lambda plus 0.0242, that is 1 angstrom is the incident wavelength I am using, say. So lambda dash will be 1.0242 angstroms. Lambda dash equal to 1.0242 angstroms. So when I am sending 1 angstrom incident wavelength, right, what is the modified wavelength? 1.02. What is the change in wavelength? Change in wavelength is 0.0242 angstroms. Means compared to 1 angstrom, what is the change? It is just 2%. Okay, 2% is a change, and the 2% change is independent of the wavelength lambda. Whatever may be the wavelength I send, the change in wavelength at 90 degrees will always be 0.0242 only. Means even if I send wavelength of 2 angstroms also, X-rays of 2 angstroms wavelength, lambda dash will be, right, 2.0242. When I send 1 angstrom wavelength, right, the change in wavelength will be 1.0242. Even when I send 4 angstroms wavelength, right, the scattered wavelength will be 4.0242. This 0.0242 is constant. Okay, now what is the percentage change you see? Okay, when 1 angstrom becomes 1.02, change in percentage change is 2%. 2% itself is small, but okay, acceptable. When I send 2 angstrom wavelength, 2 becomes 0.0242. When 2 becomes 0.0242, what is the percentage change? Just 1% change only. Okay, when I send 4 angstroms X-rays, what is the percentage change? Right? It is not even 1%. It becomes 0.5%, 0.5% change in wavelength. When I send 400 angstroms wavelength X-rays, what will happen? What will be the percentage change? 0.005%. Okay, when I send visible light, means I have to send 5,000, 6,000 angstroms. When you send 6,000 angstroms visible light, after the change, right, what is the modified wavelength? 6,000.0242 angstroms. Okay, what is the percentage change? 6,000 has become 6,000.0242, means imagine what is the percentage change? Almost 0. Negligibly small. Okay, we don't even consider that as a change also. Okay, 6,000 has become 6,000.0242, means percentage change is 0.00001%, something like that. The change is there or not, we don't have to bother. We say d lambda is almost 0 only. Okay, so we don't observe. See, in sodium vapor lamp, what are the two wavelengths we get? 5890 and 5896 angstrom. Though there is 6 angstroms difference, it's very difficult to observe them as two different lines. Okay, we'll put some diffraction rating, we'll diffract it through first order, we'll go to second order. In first order also lines will be extremely close, difficult to take readings. Okay, in second order they will be slightly separated. Okay, but when 6 angstroms difference is there, 6,000 and 6,000.0242. Okay, it's very difficult to observe. Means we cannot observe Compton effect at all. So why Compton effect is not done with visible light? Because percentage change in wavelength is extremely small. Okay, so if I use X-rays, right, some at least 2%. Even with X-rays also I am not getting 50% change or 100% change. Okay, what is the maximum possible change? 2% or 4%, that's all. Okay, right. So the Compton effect is not done with visible light. Because of this reason we use X-rays for this reason. The next point is, at 90 degrees angle, okay, I am sending an incident photon like this. There is one target electron at rest here. Our photon goes and hits this target electron, right, and photon gets scattered with 90 degrees with respect to the incident direction, say. So what is d lambda here? D lambda is 0.0242 angstroms. If I send 1 angstrom X-rays, okay, what do I expect? The wavelength here lambda should be, right, 1.0242 angstroms. But when people have measured carefully, they are not exactly getting 1.0242. Okay, there is something called 1.0243, 1.02, okay, 41, 1.0240, 1.0244, like this. Means the wavelength of Compton shifted X-rays is not exactly 1.0242 as predicted by Compton, or what the theory, the derivation what we have done. There is some small spread in the wavelengths. It is right instead of 1.0242, 0.0243 or 41 or 40 or 44. Means I am not getting exactly the same wavelength. What is the reason? This is known as the spread in the wavelengths of Compton shifted X-rays. Okay, Compton shifted X-rays. Spread in the wavelengths of Compton shifted X-rays. Why that small spread is coming? Why are you not getting simply exactly 0.0242? Why are you getting 0.0241, 0.0244 like that? Okay, what is the reason for that? Means the assumption made by what you call Compton was that the target electron is assumed to be at rest and is free. Okay, why did he consider free electron? We have seen, right? He assumed that the target electron is at rest, but inside any atom, no electron will ever be at rest. No electron will ever be at rest. Okay, right? Nucleus here, electrons will be revolving around the nucleus like this. Means electrons momentum, right? P equal to mv. Okay, right? V is velocity, which is a vector. Momentum, when the electron is revolving around the nucleus like this, though magnitude is not changing, direction is changing. In a vector, even when direction changes, we say vector is continuously changing. So the momentum of the electron around the nucleus is continuously changing. Now when I send a photon like this of some energy h nu, this photon may go and collide with the electron in any state. The electron is supposed to revolving like this. When the electron is here and it is going like this, our photon may go and hit the electron in this state. In this case, momentum is like this. Our incident photon's momentum is like this. One type of conservation of momentum principle. Okay, transfer of momentum takes place, kinetic energy takes place, some effect will come. Our photon may as well go and hit the electron when the electron is in this state. When the electron is moving like this, at that moment instant, our photon may go and hit it in backward direction. You can just imagine, you are going on a motorcycle, somebody is coming and hitting you exactly at 90 degrees. Okay, one type of effect will be there. You will break your leg. Okay, somebody is coming and hitting you right from the back, coming with more velocity. Okay, you will fall down. This time, the difference will not be that much. You will simply break your finger only, say. When somebody is coming and hitting you exactly right in opposite direction and hitting you, the effect will be more. Okay, means that momentum exchange depends in the direction in which the incident interaction is taking place. Okay, when both two perpendicular objects are colliding, one effect will be there, one type of momentum exchange. When two oppositely moving particles are there, relative velocity is more, another type of momentum exchange. When particles going side by side, going hitting each other, another type of momentum exchange, kinetic energy exchange will be there. So our photon may go and hit the electron. In one atom, the electron may be here. In another atom, at the time of the collision, electron may be here. In another atom, electron may be exactly coming in this direction. It will be in exactly opposite direction to the incident photon. Okay, when the electron is in different states, right, and the photon goes and collides, different types of exchange mechanisms. Okay, momentum exchange will be different in different cases. Kinetic energy, right, exchange also, energy exchange also will be slightly different. That's why the wavelengths are not exactly 1.02. What did Compton say? Compton thought that the electron is at rest. So only one type of momentum and energy exchange he expected. But no electron is at rest. Electron is revolving. Electron can be in any state. When the electron is coming like this and our photon will goes and hits, one type of energy exchange. When the electron is going like this, our photon goes and hits in backward direction, and the type of energy exchange will be there like that. Different types at different positions, right? Different types of energy exchanges are possible. That's why, right, we are not exactly getting 0.0242, right, as derived by Compton, right? So small changes in Compton shifts are expected. So what is the reason for the spread in the wavelengths of Compton shifted X-rays. What is the reason now? Because the target electron is not at rest, but it is in motion around the nucleus. That is the reason. Because electron is in motion around the nucleus, right? That Compton shifted X-rays are having that small spread. Or we can say the target electron has its momentum spread around the nucleus. Okay, so what is the reason for the spread in the Compton shifted X-rays? The target electron is not at rest, you can say, or target electron has its momentum spread around the nucleus. That is the reason why we are getting small changes in 0.0242 or at any angle. Okay, right? The next point is, I have been talking about the photon only. Okay, photon, its change in wavelength, etc., right? What about the recoiled electron? What about the recoiled electron? Okay, now our photon with energy h nu is going and hitting an electron, target electron, which is at rest. Our photon's energy is h nu. Okay, initially the electron is at rest. It is having only m0 c square mass. After the collision, what is happening? Photon is getting scattered with an angle theta, no doubt. But what is happening to the electron? Electron is getting recoiled at an angle phi. Okay, here its energy is, right, its momentum is mv and its energy is now becoming mc square. Initially, what is its energy? m0 c square. It is having only rest mass energy. Now our electron is also moving, so its energy becomes naught by root of 1 minus v square by c square. Okay, now now its energy has become mc square. Where from it got that extra energy? Energy lost by photon is nothing but energy gained by the electron. Okay, so that first conservation of energy equation, right? What is initial energy? H nu plus m0 c square equal to h nu dash plus mc square. What is the kinetic energy of the recoil electron? Final energy is mc square. Initial energy is m0 c square. Whatever is additional energy, it is in the form of kinetic energy only. So kinetic energy of the recoil electron equal to, I can write mc square minus m0 c square. Where from that electron got this much of kinetic energy? That is nothing but the energy lost by the incident photon. That is nothing but h nu minus h nu dash. So kinetic energy of the recoil electron is equal to h nu minus h nu dash, or hc by lambda minus hc by lambda dash. I'll write. Okay, now take hc common. Okay, take hc common. Hc into 1 by lambda minus 1 by lambda dash. That is hc by lambda dash into lambda dash minus lambda. Okay, I'm taking LCM here. Now, what is lambda dash minus lambda? Lambda dash minus lambda is nothing but our d lambda, Compton shift. Okay, that is hc by lambda dash into, right, d lambda. What is d lambda? D lambda equal to h by m0 into 1 minus cos theta. So hc by lambda dash into, right, h by m0 into cos theta. So this is h by m0 c into 1 minus cos theta, right? C and C, they get cancelled. So if I simplify, h square by m0 lambda dash into 1 minus cos theta. That is the kinetic energy of the recoil electron. Expression for the kinetic energy of the recoil electron is h square by m0 lambda dash into 1 minus cos theta. When will this kinetic energy be maximum? Okay, when the electron acquires maximum kinetic energy, when our incident photon loses maximum energy, right, our electron gets maximum kinetic energy. When our photon loses maximum energy, when theta equal to 180 degrees. Okay, when theta equal to 180 degrees, cos theta is, cos 180 is minus 1, 1 minus half minus 1. So maximum possible kinetic energy for the recoil electron, Ke minus maximum equal to, Ke minus maximum equal to, when this becomes 2, okay, that is 2h square by m0 into lambda dash. This is the maximum possible kinetic energy for the recoil electron. Okay, so these are the important aspects in Compton effect which you have to remember. Okay, questions are straightforward questions only. Okay, right, if a question comes in Compton effect, like last year Jam 1 question has come in Compton effect. Okay, right, a straightforward question has come. We will see that in the next video. Okay, so this is about Compton effect and the discussion about all possible variations in there. Okay, next one, the problem which came in 2020 jam. Okay, 5 non-interacting particles are present in a one-dimensional box of width A. One-dimensional 1D box. What is the expression for the energy levels are quantized? What are the quantized energy levels for a particle in a 1D box? Right, En equal to n square pi square h bar square by 2m a square, where a is width of the box. So ground state energy means I'll take n equal to 1. Okay, so E1 equal to, right, pi square h bar square by 2m a square. What is the next allowed energy level? This is ground state, n equal to 1. Next allowed energy level, n equal to 2. You put n equal to 2, the second energy level will be 4 pi square h bar square by, right, 2m a square. Okay, right, for n equal to 3, the energy levels will be, put n equal to 3, the energy levels are E3 equal to, okay, E3 equal to 9 pi square h bar square by 2m a square. Okay, now what did he say? He says that there are 5 non-interacting electrons. Okay, electrons are fermions. So Paulie's exclusion principle. Okay, one energy state can accommodate only 2 electrons with opposite spins. Okay, so what happens when I put the first electron? It will go and occupy the lowest possible energy state, that is n equal to 1. Its energy will be pi square h bar square by 2m a square. I will throw the second electron also into the sample. That electron will go and occupy the first energy level only with opposite spin. So its energy also will be pi square h bar square by 2m a square only. Okay, now I'll put the third electron. What happens third electron? Third electron cannot go and occupy this level. Why? It will violating Paulie's exclusion principle. Okay, these 2 electrons are having opposite spins. Third electron cannot go and sit beside these 2 electrons. Okay, Paulie's exclusion principle gets violated. So whether it likes or not, the third electron is forced to go and occupy the next level. Okay, so it will go to n equal to 2 level, means its energy becomes 4 pi square h bar square by 2m a square. Now I'll put the fourth electron. Fourth electron can go and sit beside the third electron. It cannot go to n equal to 1. So it goes and sits beside the third electron with opposite spin. So its energy also will be 4 pi square h bar square by 2m a square. What about fifth electron? These 2 levels are completely filled. Okay, the fifth electron cannot go and sit in what you call this 4 electrons lap. It is not possible. It has to go to the next higher level, whether it likes it or not. Okay, so it will go to the third level. Third level energy is what? 9 pi square h bar square by 2m a square. Okay, he is asking what is the maximum energy of the particle. Maximum energy of the particle is 9 pi square h bar square by 2m a square. That option is also there in the paper. Okay, so the answer is simply 9 pi square h bar square by 2m a square. This is one problem. Okay, it has come in the exam, you'll answer and come on. Okay, one problem when you are preparing, you can convert that into 3-4 different problems. Okay, we ourselves should modify what happens if the same question comes in another way. Okay, that should be the preparation strategy for every competitive exam. Okay, you see one question in some previous IIT paper. Next time, how that question can be modified in different ways also you should be able to think. One question should be split up into 4-5 different questions. If I am the examiner and I am asked to set the jam paper, right, I'll simply modify this question. What is the total energy of the system? Okay, total energy of the system means you have to add the energies of all particles. Okay, 1 h bar square, 1 E1, 2. Okay, this one is 4 plus 4, 8, 8 plus 2, 10. This one is 9. Okay, means 19, right? Pi square h bar square by 2m a square is the total energy of the system. Okay, how many particles will be there with energy? 4 pi square h bar square by 2m a square. Okay, 2 particles will be there with energy, right? 4 pi square h bar square by 2m a square. How many particles will be there in ground state? Only 2 particles will be there in the ground state. Okay, right? Like this, you can modify. We can modify the question ourselves. Like in what happens if that modification? What else you can expect here, right? So what is the total energy? how many particles, what is the total energy of the particles in the second energy level, what is the total energy of the particles in the first energy level, what is the total energy of the particle in the third level. Okay, how many particles will be found in with energy 16 pi square h bar square by 2ma square. Okay, question comes like this: how many electrons will be found with energy 16 pi square h bar square 2ma square? There are only 5 particles. Okay, only 3 levels will be occupied. So highest energy itself is 9 pi square. So 16, there won't be any electron with 16 pi square h bar square by 2ma square. Okay, like this we can ourselves we can modify the question. That's how we can prepare for the exam. Okay, thank you. We'll continue the de Broglie's concept in the next video.